Hi, my name is Tom Brown. I'm the director of Borderland Sciences Research Foundation in California. And today we're in our top secret laboratory hidden in the vast suburban wastelands of Southern California. And we're taking a look at Tesla's longitudinal electricity. The electricity in general use today is transverse electromagnetism. And what Tesla was experimenting with in his types of experiments was called longitudinal dielectricity, a polar opposite to that. And we're doing advanced research into that type of electricity. Now we'll take a quote here from the book Experiments with Alternate Currents of High Potential and High Frequency, which has an appendix called The Transmission of Electric Energy Without Wires. And to quote Nikola Tesla, toward the close of 1898, a systematic research carried on for a number of years with the object of perfecting a method of transmission of electrical energy through the natural medium led me to recognize three important necessities. First, to develop a transmitter of great power. Second, to perfect means for individualizing and isolating the energy transmitted. And third, to ascertain the laws of propagation of currents through the earth and atmosphere. Now, the transmission of great power was, of course, carried on by Nikola Tesla in his Colorado Springs experiments, which led to the building of the Wardenclyffe Tower, which was to transmit electrical energy around the Earth. And the second point, the means of individualizing the currents, was in his experiments with harmonic resonance circuits, such as you're going to see today in this video. And third, the laws of propagation are his one-wire and wireless power transmission, where he demonstrated longitudinal currents rather than the transverse currents, which he did not feel were all that swell for propagation of electricity. So here today we're going to see some experiments in this, and now to give you an introduction to the experiments by showing Tesla's patent and the schematic that we're using is Peter Lindemann, director of Borderland Sciences.
Hi, I'm Peter Lindemann, Vice President of the Borderland Sciences Research Foundation. Today I'm going to explain to you the basic experimental setup, which we're going to demonstrate in a little minute. Over here we have a schematic drawing of our experimental setup. And down here, I'd like to first bring your attention to Nikola Tesla's patent number 649621, which was granted on May 15, 1900. Basically, this describes the experimental setup which we will attempt to show you today. And I'd like to describe it for you right now. This is a transmission and receiving system for what he called his wireless power transmission. The exact name of the patent is Apparatus for Transmission of Electrical Energy. And it consists of a generator system which produces the appropriate types of currents, which goes through a two-loop primary on this device here. This is the thick, darker line around, which you can see on your television screen. Inside here is a flat spiral coil, which is connected to ground at the outside of the spiral, and on the inside of the spiral is attached to what he calls the termination, which in the case of the Colorado Springs experiment was a ball, a sphere that was high up in the air. The receiving apparatus is identical in nature, consisting of a termination, a flat spiral coil, and a connection to the ground. And the outside primary or secondary of this system is attached to the loads. So that describes the patent that Tesla was granted in 1900. Now what I'd like to do is describe for you the exact apparatus which we will be testing for you today. Our generator system consists of this much of our diagram here, which includes a medical Tesla coil circa 1920, which produces our supply of electrical induction. We also have a capacitor to create circulating currents in this, which is a 0.001 microfarad, 15,000 volt capacitor built by the Faradon Corporation. And we have two hydrogen spark gap tubes, 1B22 here. And this creates a negative resistance which helps to accelerate the wave. So this is what we're using to supply the appropriate currents to our primary of our coil here, which is a two-turn flat coil made out of sheet copper. This showing the two turns, just like the two turns shown in the diagram here. Our secondary is made up of, our termination in this case is a neon bulb, which acts as a plasma, which in these low power systems works better than a large sphere. That's connected to our flat spiral. In this case, our flat spiral is made out of Teflon-coated silvered coaxial cable, of which we're just using the outside shielding, the silvered shielding, and not the inner wire, because these currents operate primarily using what's called the skin effect. And then our output, which is at the outside of the flat spiral, our output here. And now we will run a number of experiments attaching various things to our output here, showing various behaviors. Our second apparatus is identical. It has an input at the outside of the flat spiral made out of silvered coaxial with Teflon coating on it, and going up to a second termination, and a second series resonant harmonic resonance circuit, which is tuned exactly the way our transmitter is, with two turns of flat copper sheet and connected to a second 0.001 microfarad capacitor identical to this one. And so these two primary circuits, one of which is energized, the other of which operates in harmonic resonance, makes up our circuit. We will attach loads to this output, as well as putting various devices in here for the transmission of our electric currents. So this is our test setup. And now I'd like to introduce Eric Dollard, who will first show us the actual physical setup of our test apparatus today, and then we will run the experiments. Eric?
Hi, my name's Eric Dollard, and I'll be running the experimental setup for the Tesla wireless transmission system. We'll go through our diagram here on the board, which Peter showed a little earlier, but now we'll show you the actual devices. For a supply of electrical induction, we have an old Fisher Medical Tesla coil from roughly around 1920 to 1930, which in itself is a complete little wireless transmitter, but we're just going to use it to charge up our high voltage capacitor shown here on the diagram, which is an old mica capacitor from shortwave radio transmitters used also around the 20s. We use these kind of capacitors because they have a very low inductance and very low hysteresis losses, and can deliver really strong high power impulses. And here's our 1B22 hydrogen fibertron tubes that we're using as spark gaps. You can use a number of other things for spark gaps, such as quenched gaps or rotating commutators with these tubes. Work pretty good for this, and they don't put out a lot of light or noise, and the negative resistance of the hydrogen plasma increases the rate at which the discharge occurs and produces stronger transients. Our primary coil is two turns of copper right here on the large transmitter unit. Let's hold this up a little bit. You might be able to see actual strips of copper on the primary, and then our secondary resonant coil. And of course our coil is shown here on the diagram. I might not want to point out that this coil is not just a simple inductance coil, nor is this thing just a simple transformer. The inner turning capacitance plays a very important part in this coil to give it a very strong resonant frequency. And the resonant frequency of our primary oscillating circuit here is chosen to fall on one of the fundamental harmonics of resonance of this complex network of mutual inductions and capacities which the spiral makes up. And we'll go through a frequency sweep and what have you later to determine exactly what these are. Our termination is an argon bulb here at the top. And our output terminal on the outside of the spiral comes down here to a little banana plug which we can plug various things into. This coil here serves as a loading coil to help couple the energy out into the rest of the system, increase the efficiency. So this basically would simulate maybe the impedance of the earth or the transmission medium in general to give the coil something to work into. Okay, to start off with, our transmission path is a simple plasma column, and then we have our conjugate receiving coil, which has exactly all the same characteristics except it's wound in the opposite direction. And it finally ends up with its final tuning capacitor. The same tune circuit as the primary, so naturally we're going to get flow between the two because of their resonance, and then we have the end result, which is a 15-watt light bulb, which will be our resistance load. We'll connect across the output here. And we'll have Tom turn the switch on and we'll see it go. So of course the load is lit, and we have a single wire path going from the receiving transformer through the plasma column, to the loading coil, and off to the transmitter coil. Hence the single wire method of electrical transmission. Okay, we'll take a brief pause here and we'll get into our experimental setups. Okay, our first experiment is we'll run the light bulb conventionally in the electromagnetic fashion where the circuit is a closed loop or a true circuit. And then what we're going to do is we're going to pull the plug and see if the light bulb still lights up. And we'll start off with the conventional circuit method, energize it, and of course the bulb lights up. Now what we're going to do is we're going to pull the plug on the bulb. We find the light bulb still lights up, so we're starting to get a rather novel thing going on here. You can see the wires become quite energized. High voltage is on it. The neon bulb readily indicates there's quite a bit of charge. Okay, turn off the power. Now what we're going to do, let's go back to our diagram here. What we did in disconnecting the plug is we switched to this configuration here where there's no connection on the other end of the light bulb. Okay, now what we're going to do is hook an amp meter up to ground. We have a Simpson, in this case, thermo amp meter, which is not very susceptible to spurious readings because it takes actual heating to produce a result. And we're going to plug this into the output end of the coil and see how much current this system delivers to the ground. Reference to our drawings over here, this is now our setup. And if we energize the system, find that we have roughly 0.68 amperes of current flowing out of one terminal in the ground. Hence the Tesla wireless transmitter. Turn off the power. Okay, and after a brief pause, we're going to go through our experiments where we hook various devices in between the two coils and see how they propagate these currents. Okay, now we have our two coils set up with our series path, our terminals. In this case, our terminals will be here on the workbench. terminal from the transmitting end through the loading coil, and the terminal to the receiving end, and of course we can connect various items in between. And at the receiving end we have a pickup thermomilliamp meter to measure the amount of induction the device is receiving, and that'll be our determination of how effective each of our three items are here for the transmission of currents from the transmitter to the receiver.
So can you just describe this situation here? What do you got? You've got two turns of
14 gauge wire and a little magnetic pickup coil that determine how strong the field is around the coil. And of course that gives us an indication of how effective each of the items is in conveying the current from the transmitter to the receiver.
All right, great.
Okay, we'll start off with just a regular wire connection and go into power supply, and that'll give us the reading on a milliamp meter, which is, can you read it, Peter?
About half scale. Looks like 72 millionths.
72 radio frequency milliamps. Okay, we'll turn the power off. The next thing we'll put in is a plasma column. And we'll energize the power. And the meter will read again.
Slightly less, about 65, 66.
Okay. The next thing we'll insert in is a series parallel bank of incandescent bulbs.
Now it's a lot lower, about 50 milliamperes.
Okay, so we can see now we have a definite difference between transmission through a plasma column and transmission through what would represent an effective length of conventional transmission line, in other words, wire with resistance. Plasma column tends not to have any resistance, where the conventional transmission medium tends to exhibit resistance. And of course, in direct connection, all these factors are so small that they don't really appear. Now, what we're going to do is we're going to get into some of the effects of the illumination that comes off of these incandescent bulbs, which contain vacuum, when run off of these currents. And we're going to do a comparison between a bulb running off of 60 cycles and a bulb running off of high frequency right next to each other. And this will lead us into our second Tesla patent, which is the transmission of electricity by radiant means. And we're going to show how DC can flow through space with only one wire. So we'll take a brief break here and set up our new experimental apparatus. Okay, here we have two conventional light bulbs, and they're 15 watt, 120 volt. We'll bring one up close to the camera here so the construction of the bulb can be seen.
It's too close. Yeah. Just back there is fine. And I'm gonna get a sharp focus on this. You have to go farther away even. They're about there. That's fine. Yeah, so you can see the filament. It's a little ring filament. That's great.
Right, and one interesting feature of these bulbs is they have a very big vacuum space, which is not usually found in most light bulbs, and they're not filled with gas like most light bulbs are. These are vacuum light bulbs. So we'll have two of them here. This one and this one. One will run off of conventional 60 cycle alternating current, and the other one will run off of the longitudinal current. And we can see the brightness is pretty close to the same. Now let Tom come over and see if he experiences any difference between the light of the two bulbs.
Okay, well, one thing I do notice just visually, and we really can't record this because we don't have the proper detectors, but just the character of the light. This the electromagnetic light transverse looks somewhat reddish to my eye, and this looks somewhat bluish. And it just feels kind of hot, like a regular bulb. But on this one here, I feel a pressure coming off, a charge and a pressure, which I felt a little shock there also. And but the character of the light is definitely different. There is a distinct pressure, and the higher up we turn the power going in, the stronger the pressure is. And now we'll give another demonstration which shows another characteristic of this opposite to the pressure.
Okay, one other thing I'd like to point out is the fact that this situation over here is very stable and quiet. We have, according to the Variac, 115 volts across the bulb. This light bulb here, the socket, is arcing over inside. indicating there's several thousand volts across the bulb. So we can start to see some difference happening here. Now what happens is when you have gas in the bulb, as well as the filament, this very high voltage that appears across the bulb energizes the gas, and you end up with what would be a full spectrum light bulb, which still retains its incandescent characteristics. But these bulbs being vacuum, we can't really fully demonstrate this. Now what we're going to do next is we have a force coming off the bulb, then we can study this force. And what we'll do is turn the power off for a second here, and we have a little piece of copper strip dangling from insulated tape. Let me just center this up here a little bit. I can help.
No, it's got to be lower.
Why not? Okay, first we'll bring the strip near the Tesla current bulb. Turn it on. See the traction.
It'll only turn off on a couple times, yo.
Move it slightly farther away, and let me get a real tight focus on
Turn the
this.
power on. I'll bring it near it. You'll see where it pulls in. You see once you hang it on there. Okay, now what we'll do next. Stuff.
So that's just a piece. That's a piece of copper foil,
Copper foil, copper tape,
hanging on a piece of
masking tape.
masking tape.
Turn on the conventional, and of course you see we get no effect.
Even closer, right?
Right up to it, and as can be expected, there's really not much of anything happening there.
Right. Okay.
Just a little bit of residual charge that was left on the metal. We'll go back to this one, and we can see traction. Okay, we'll turn the power off. Now we can say, well, it's just high voltage. But what we'll do, we'll put this point here,
So now what you're bypassing the light bulb.
bypassing the light bulb.
So we're just running the current past
just
the
going to
strip.
have the high voltage itself next to the thing.
Okay.
Turn it on. No traction. So as we can see, it's definitely charged there. Bring the point right up to it. No desire at all to be attracted to it.
So what you're saying is that the attraction is related to the action that's happening in the bulb.
Right. The bulb is producing rays. As well as light rays, it's producing another form of ray which exhibits mechanical action at a distance. The human body experiences it as pushing out, but material objects experience it as pushing in.
Okay. Can we see that effect one more time? Let me start with it just a little bit farther away. We can turn this just so we can have an idea. And let me just focus right tight in there. Okay.
Ready?
Pulls it right in.
Here it goes.
Okay, now what this does is bring us to a whole new area of Tesla's wireless power transmission, which we'll get into part 2. And we'll go back to the original patent and start out from there. So we'll take a brief break here.
Okay, here we're looking at Nikola Tesla's patent number 685957, apparatus for the utilization of radiant energy. Now, what Tesla was very interested in was the propagation of light and currents, beams of light and current through space, and also on how to receive these, both send and receive. And here we see the apparatus for receiving, which is basically a small condenser, one end to ground, the other end up into space, and you could pick up various cosmic radiation, such as solar. And Tesla also claimed that some of these radiations from outer space moved at 50 times the velocity of light, although there's no exact verification of that. And here we see an apparatus, a carbon arc, charging this. And down at the bottom here we see a light bulb, single wire bulb, energizing the apparatus. And what we're going to do now is show you this experiment, charge a capacitor from a bulb and show you the discharge from it.
Okay, what we have here is a capacitor, television doorknob capacitor, 500 microfarads at 20,000 volts. And it's connected to ground, sink. In the other terminal of this capacitor, we're going to bring near this light bulb and see if we can charge the capacitor up like Tesla did with the radiations or forces emanating from the light bulb. So we'll energize the circuit. And we'll hold the other pole of the capacitor some distance away from the bulb. Okay, let's see if we get a charge on it. We have a small neon bulb here. Capacitor seems to want to go away. I don't know if you caught
A
it.
small
Yeah,
flash.
just a small flash on the neon bulb.
Let's do it once more.
So let's start by shorting the capacitor completely to handle the doubters that we don't start with a charged capacitor. Okay, so that's completely shorted to ground, both ends, so that you can believe that this is an absolutely dead short. It's an uncharged capacitor.
Prevent it from rolling away. Okay, let's try it again.
This time let's leave it near there to try and build up a bigger charge.
Okay, I haven't determined exactly what part of the bulb is out that's charged yet.
And bring it down by the side so it's closer to the cylinder.
The sides is where I feel the greatest pressure.
Yeah.
Okay, I think that'll do it.
Okay, and we'll try and keep the neon bulb in our view here, so if it flashes at all.
Little
Very
tiny
small
flash.
flash that time. Let's try it one more time. Okay, let's try it again. One time I got a very large snap out of it. Yeah,
There we go.
pop.
Okay.
Okay, so what it wants is to be held in one more spot, or one particular spot, not moved around. So it indicates the charge is different in different directions. Okay. Now, what we should do is bring it near the wire, or one of the hot points around here, and make sure it's not just the electricity itself that's charging it up. Corona there, getting the currents that are flowing to the capacitor. Very small flash. Let's try it one more time. Corona is going to cause a certain amount of rectification because it's an electrical conductor, so we will expect a small charge to exist on the capacitor. Now we'll go back to the light bulb. Okay. Snap. Definite difference. Okay, one other experiment we'll do is we'll bring it near the very high voltage of the neon or argon lamp. And there'll be some residual charge, I'm sure, but no snap. And we'll go back one more time. The light bulb. Okay, now what we're going to do next, our next test setup, is we're going to attempt to demonstrate the actual transmission of DC through free space.
So basically what we've just seen here is that fairly conventional light bulbs produce radiations which are not seen when the same devices are run on ordinary 60-cycle AC
That's
electromagnetism.
Right. But what's involved here is what are called impulse currents, and we usually use are alternating currents.
Uh-huh.
So there's a distinct difference.
Mhm. Now, how is this related to like the types of energy that runs in your body?
Well, that's a good question.
Well, one of the things I thought is that all the impulses in your nervous system are actually impulses. There's like what tells your heart to beat and everything. These are impulse currents
Oh,
that run in your
correct.
system.
Right, they're not alternating currents, they're periodic impulses.
Right. Same with nerves firing and things
Right.
like that. These are all impulse currents. So this running these systems on impulses is much more like the way living things operate.
Exactly.
Well, another observation on that is that the character of the light coming off of these bulbs with the Tesla currents on them is much more akin to the type of light coming from the sun, where there's a radiant pressure outwards, and it seems to be a natural type of light, much more beneficial to the body. This type of light would probably go quite well in hospital operating rooms and schools, things like that. It's a very open-ended area of research.
Right, it could be demonstrated, even though we're not capable of doing it here right now, but it has been demonstrated before that it does take less electricity to produce light by this method, particularly when gases are in the bulb. One thing we can also show here, so if the bulb's back up in series, can you hand me the small green clip? Conventional series circuit. Going back to our original demonstration where we pulled the plugs, we'll do that again when we turn the power on. Okay, see the bulbs light up, of course they're all in the series path. You notice one starts off a little brighter than the other. Okay, turn the thing off, turn it on. And of course the light bulbs still light up. And we don't feel the pressure quite as strong around it now. The intensity of the filament is not as great. It's definitely there. We'll do a quick capacitor charge off of that, and then we'll get into the next part of our experiment. Oh, it's a little bit less than the sun, even though the voltage is higher. Yeah, it's much smaller, but still a spark. Okay, we're going to put our next setup together now. Okay, we have our next test set up here. We'll start with our electrostatic voltmeter, which is an unbled MOSFET input going to a bridge amplifier, which will read out on our center scale voltmeter. And that connects to our antenna here and ground, which is down here underneath. And then on this end, we have a source of high voltage direct current, in this case of positive potential, and an electrostatic power supply down on the ground there, a 0 to 30 kilovolt rectified radio frequency type power supply, which we can select the polarity. We've chosen positive for this because it seems to work the best. And what we're going to do, we're going to focus back on the meter. I'll get up here so I can see the meter. And then Tom is going to crank up the power supply voltage slowly and read off the voltages on the voltmeter as he goes up.
Here we're about 5 kilovolts, 7 kilovolts, 9 kilovolts, 10, 11,
The meter's starting to
13.
jump, and I can hear corona coming off the high voltage point.
we're at 15 kilovolts, 16, 18,
And the hiss now is quite strong.
20.
Off the transmitter lead.
25. I'm up to max, which is about 28 kilovolts.
Okay, and we're not really getting much current reading other than just a displacement current of the varying potential. Okay, bring it back down.
Okay, power off.
Now we're going to attach this fluorescent lamp to the receiving terminal. And this single terminal neon tube to the transmitting terminal is our plasma columns. And then we're going to try this experiment again. Okay, the meter now responds a little better. What
So
voltage?
start reading more.
We're at 4 kilovolts, 5, 6,
Okay, hold it right there.
About 6.5.
So this is already working.
It's already
Better than
working
3
6.5
times better.
kilovolts. Okay, bring it up a little more.
What do you got there?
I'm at 8.
Okay, and we
Let
got
me turn the sensitivity down here
the
now.
meter peg.
Okay, let's just hold it right there for a second. So now the meter stands, even though there's no variation in potential, current propagation still exists. And we can't see any glow in these tubes either, which is rather peculiar. It's a dark
Now,
discharge.
You walking behind there made the meter swing the opposite direction. So do that again. Put your hand, okay, that doesn't change it. Oh yeah, it changes its
Motion.
Well, by motion in the electrostatic field, of course,
Right.
it's going to introduce alternating currents.
Now it just swung over to the opposite side,
It's holding.
and it's holding. So back away again. Yeah.
Switched over. Oh, your feet by the ground.
Oh, yes, I'm charged up being insulated.
Yeah,
What's happening?
there you go. So it's still propagating a continuous current.
Right.
So this demonstrates what? The wireless.
This represents what Tesla was thinking about transmitting DC through space.
DC through space.
Right, and using the appropriate asymmetrical impulse currents at the transmitter end and synchronous converter at the receiver end, one can get very effective transmission through space of DC, which we indicated already existed close to the light bulb at the television doorknob capacitor.
Okay, so you want to turn that off, Tom?
Turn that off. Put this thing back on 0. I had to rebalance it in order to get the scale. I want to crank it up again one more time just to see it do it again.
Okay. Quick reaction there.
There it is.
It's come to about 7.5 there. 7.5 kilovolts. 10
pins the meter.
Okay.
Down to about 4 there. Down to 0.
Okay, well that concludes our experimental demonstration current transmission. What we'll do next is give the dimensions of the apparatus and a practical application of one of the coils operating a shortwave radio receiver with no antenna tower.
So this pretty much vindicates Tesla's patents. A lot of people have taken a look at these patents and thought that this was all fairly novel and interesting, but I've never seen anybody duplicate these experiments before. Have you? Besides right here in this laboratory?
No, because no one is really building the apparatus the way Tesla intended, and also everyone tries to explain it away with conventional laws of physics.
Mm-hmm. So what would be a conventional way of explaining this away?
Well, it would be that ions are being carried from here to here, but we saw even when we had a heavy corona on the point, we didn't get a continuous current reading on the meter. Okay, now we found earlier, and we were not able to duplicate it this time, probably due to the severe humidity in the room, that even with no tube hooked up, you will reach a certain threshold where the meter will read.
Mm-hmm.
And Tesla pointed out that when you exceed a potential gradient of 12 million volts per centimeter, okay, in this case it's kilovolts per millimeter of curvature to get the same quantity, that current would flow through space and propagate outwards, building up a conductive media behind it. And he had figured this way he could tunnel a path between the transmitter and receiver to carry direct current or impulse currents.
Mm-hmm. But not alternating currents.
Not alternating currents. He didn't plan to do it with alternating currents, it'd be impulse currents. Most of his work is with impulse and oscillating currents. The limiting case of an oscillating current with no dampening being an alternating current, and the limiting case of an impulse current with no decay factor to it or rise or fall would be a direct current. So impulse currents and oscillating currents are what Tesla was working with, and what we utilize are direct currents and alternating currents. So there's a distinct difference, all 4 of those being the general number of, 4 currents, general currents of existence.
So what you're saying is that the general way of explaining this away is fairly well shot when we connect it to the plasma tube there, and it works much better.
Right, and the plasma tube remains dark.
Exactly.
And the plasma tube on the receiving end obviously cannot be glowing.
Correct, but that makes the receiving end receive better.
Receive better. And there seems to be, we take the plasma tube off of the receiver, energized here.
Yeah, I can come back up.
And it'll come back up. We'll probably still get a reading to some extent. Let's just make sure.
Okay, with 5 there. 10.
So you're all the way up to 15 kilovolts.
And the receiving is much lousier.
Oh, now you've reached the threshold point and I can hear the corona.
Yeah.
We're getting a little transmission. Keep on going
I'm
up.
at 28. I'm up all the way.
Okay. Now most of that will be the radio frequency of the corona producing displacement currents in space, which is not direct current anymore.
So yeah, there's a threshold that came down about 25. It just dropped.
So we leave this to the audience to explain. I mean, those that want to explain it away will be fine and dandy. You're not going to get too far in Tesla's work trying to explain everything away and saying he was wrong. But if you develop the attitude that Tesla was right and try to systematically duplicate his experiments, as you can see with relatively simple stuff such as fluorescent lamps and old insulators and junk meters, that it's quite possible to duplicate his experiments. And none of these things are tuned to each other either, and the little fine details worked out. We're already getting results here with the very basic beginnings. No lamps or tubes specially made, coils not harmonically balanced so that all the odd order harmonics add up in the proper phase relationship. None of these things have been dealt with yet because we just don't have the money, time, material, manpower, etc. to do this. But just the basic duplications and copying of the patents already indicates to us a good start.
Okay. For those of you who are interested in duplicating any of this research, I'd like to describe for you the construction of the coils that we've been testing. Over here, we have one of the Tesla coil apparatus built by Eric Dollard, facing up, and I'd like to just describe for you its actual construction. Here we have the primary, which consists of 2 turns consisting of 3 layers of 1 inch wide by 10 thousandths of an inch thick bronze strap, so that each turn is made up of 3 straps of that dimension. The secondary, which begins here, or at the output, and ends here at the termination, consists of 20 turns to here, and then another half turn around here of Teflon-coated silvered coaxial cable, which is approximately 85 thousandths of an inch in diameter. The outside dimension of this secondary coil is approximately 18 inches, and the inside diameter is approximately 13.5 inches. Each turn begins here and goes all the way around on the bottom, and then comes to the top of the same layer, and then goes all the way around again, and then comes to the next inside. So the first 2 turns are here, second 2 turns are here, third 2, fourth 2, fifth 2, etc. So that each adjacent winding has, you can zoom in on this section right here, Tom. The first winding goes all the way around in the outer slot here, and then the second winding is right on top of it, so that these 2 windings are very close to each other. Then when it comes around to here again, that moves to the next inside dimension, and 2 turns are wound there, and then 2 turns here, 2 turns here that are on top of each other, so that there are 2 turns that are very close to each other, and then slightly farther away. This creates these relationships of mutual capacitance and induction, which Eric was talking about earlier. And the coil basically comes to a 20th turn ending here, and then a single turn comes out through here and goes to the termination, which in this case is an argon bulb. Primary is attached with many single strands to our 0.0001 1 microfarad capacitor. In this case, we're using a smaller one because we're about to take this unit as our receiving unit out into the field to see how far our other transmitter unit can transmit. So this is the construction of both of these coils. The other coil has these primaries and secondaries wound in the opposite direction, so that these are complements of each other. So now you know enough to build one yourself.
One thing that should be pointed out is the total volume of copper used in the secondary should equal the total volume of copper used in the primary.
Okay, but in this case we've got bronze here and silver.
Yeah,
so
it's
in
a
other
little
words,
bit
metals.
different.
Yeah.
So what you have to do is you have to compensate for the skin effect to figure how much is used. And basically in frequencies of these type of coils, it's not good to use conductors with a thickness much greater than 10 mils. Otherwise you have to readjust your volume.
Mm-hmm.
But Tesla found that when the copper weights or conductor weights are equal in the primary and secondary, that you got the best effects. And then weight could be best expressed rather than weighted volume in this case, and then with the skin effect, it finally resolves to equal surface areas.
So the surface area of the primary equals to the surface area, the effective surface area.
Yeah, that's what eventually you would strive for, but it's the simplest way to do it is by volume.
Mm-hmm.
And these are designed on a per volume basis, equal primary and secondary volume of copper. The reason that all the little wires are used to connect to the capacitor is to eliminate the skin effect and reduce the stray inductance in that area.
So that the magnetism stays
inside
in
the
coil.
enclosed loop around.
Could you hold that up so you show how it's connected onto the capacitor? It's not real clear.
Can you tilt the thing up maybe? Yeah.
Okay. Focus in here.
So even though the currents and voltages might be small in the receiving coil, you still have to use high voltage and high current apparatus to keep the resonant frequency sharp. It's very important that the effective resistance of all this be kept very low. That's the reason for using sheet copper or multiple strands of smaller conductors. You might want to tilt the thing up sideways and show how the yardsticks were notched and the insulating loop that holds it up to give the experimenter an idea how to do mechanical construction.
Okay, get a pretty good shot of the notches there.
These were carefully run through a table saw that had the blade at the specific depth, over and over and over and over and over and over and over to create each notch.
Yes, I spent many hours doing it.
Yes, exactly.
I remember.
So this is what the experimenter has to do. This is the boring side of science.
And then the outside loop is made of phenolic type insulating material that was cut out of a large drum. And that basically holds the whole thing together. And of course the object is supported in the air by the ceramic post insulators, which could be wood or any other so-called non-conducting medium.
So-called.
Now, of course, you want to use these things for very high voltage and high power, then you have to get rid of the wood and use all the glass epoxy where the yardsticks are. Eventually, the thing works best if you use all Teflon and silver. Those are basically the two materials to use in the construction of all this, is Teflon and silver.
Yeah, because Teflon doesn't break down.
Right, and if it does punch through, it won't crack or melt. And the silver doesn't corrode and offers the best reflectivity, but then of course the skin effect is going to have to be compensated for, and the silver strands that have to be thinner. That's one of the reasons for using the Teflon insulated coax, because they can't put the Teflon on the wire until they silver it because of the corrosive gases that are formed. So it makes it perfect for this. And of course, because of the skin effect, there's no need to have any metal on the inside, so the inside wire of the coax is never used.
If anybody wants to duplicate these experiments and has any questions, just write to Borderland Sciences Research Foundation.
Okay, I'll describe our test setup here for our wireless transmitter. What we're going to attempt to do, and for the first time, we haven't tried this before, is we're going to transmit a shortwave signal with this Tesla wireless transmitter, and then we're going to go down to the beach with the receiving coil and connect the screen to the salt water and see if we can pick it up. So I'll describe our setup here. This is similar to what we did before with the spark gap, but now we're using a CW oscillator. So what we have here is an oscillator to produce shortwave signals. Right now the oscillator is 2 megacycles, 2.955 megacycles, and the oscillator connects to a push-pull cathode follower, which delivers a push-pull output that we're connecting across our primary arrangement, this being our main capacitor here. Okay, we have an RF milliamp meter here, 0 to 100 milliamps, with a shunt across it to multiply it by 2, and that connects to the neutral lead of the coil, which is right here. You might want to zoom in on that so we can see that the coil actually comes off there. Capacitor out of the way here.
Okay.
You see the final turn, the beginning turn, depending upon how you look at it. The coil comes around, connects to the neutral lead. The other end of the coil, in the middle here, comes up and connects to the neon bulb. You see the neon bulb is lit. Even though the video seems to make it look like it's lit all the time. So what we'll do is we're going to sweep through. Okay, let me point out that the meter again is connected to the sink. You might want to sweep over and show it's grounded to the sink.
Okay, there's a sink.
Get the lead up so we can see. It's actually connected.
We now know that it's connected to the sink.
Now ideally the coil should be very close to the ground and connected to a zero inductance grounding system, in other words a plane. But we have to use this lead for now on the bench here, so that introduces some stray inductance and throws the frequency off. Okay, now we're going to sweep through here. We'll start down at the bottom of the band. Okay, start with 1.6 megacycles. Go up, and the meter starts to rise, 1.875 megacycles is one resonant frequency. Call this resonant frequency A. And keep on going up. Rises very sharply on this one to back to the 2.945. It's resonant frequency B. Now one of these resonant frequencies will be a predominantly transverse wave, and the other resonant frequency B, will be a predominantly longitudinal wave. Any coil, any radio receiver or radio transmitter will have these two components. And as we'll show later, a radio receiver can either be used to receive through the ground or receive through the air antenna, elevated antenna or aerial, depending upon which mode of its input tuner you're selecting. And if the parasitic capacitances in the coil are reduced to a very small value, then only the transverse wave will predominate and the longitudinal wave will disappear. What we're using here is the capacitances in the coil to produce these effects. These double frequencies indicate that there's 4 constants involved, 2 inductance and 2 capacitance constants, giving a quadrature or 4-pole equation that will give us a pair of resonant frequencies, as we can see on this. Now ideally the coil should be balanced so these frequencies fall together and has only one resonant frequency, but no mathematics exists for this as of yet. And we don't know if Tesla figured this out or not. His mathematics was also very poor at the time, so he had to do it purely by empirical and experimental means. But he had the time and dollars to do it in his beginning work, and he probably achieved this, which should magnify the effect several thousand times. Okay, we're going to show our shortwave radio here. We have a small Army unit. 2 to
If you tilt it up and get a little light on it.
2 to 12 megacycle receiver. Runs off the batteries.
Focus in here.
So we have no ground connection or 60 cycle noise problem to worry about. We can take this around, battery packs in here. It's a vacuum tube receiver. And this is, we have the leads brought up that connect to our antenna input transformer, which will connect to the receiving coil. Now what we can do right now, the receiving coil's right here. Let's hook it up for calibration purposes. So you can hear our transmitter on location here to spot our frequency. So I'm going to put the receiver across the capacitor. Take our neutral terminal and just bring it out a little bit for now to set up impedance reduction at that terminal. And plug in the loudspeaker. On 29.4 roughly. It's kind of hard to see on the dial. It's not a very finely calibrated receiver. Okay, and I'll lock the dial. Then we'll take the thing down to the beach and we'll see what we can pick up. Okay, what we're starting with here is we have a copper screen sitting in the salt water.
Okay.
Lead comes up, connects to the neutral lead of the coil.
Right.
And we have a shortwave receiver hooked up to the capacitor directly.
Basically the same setup as a lab bench, but instead of the sink, we're now hooked to the ocean.
Okay, and the laboratory is about 3,000 feet that way, behind these rocks.
Okay.
Now, can we hear the tone?
Yes.
You sure? Let's get right up to it so you can hear it.
Without a doubt.
Okay, let's move to the receiver so we can see the frequency dial. Okay, we're in there. Okay, and it shows the coil's working. Disconnect the lead and the signal drops way down.
Okay, let me back off here and get a full shot like these. Okay.
So I think that pretty much demonstrates what's going on here. So we'll go back to the laboratory and wrap up with the conclusion.
Well, that concludes today's practical demonstrations into Tesla's longitudinal currents. As you can see, this type of experimentation is quite easy to do. All you have to do is go back and see what Tesla said and reproduce the experiments, and you'll be amazed at the results. And which that raises a big question with all the work going on in Tesla these days. Why isn't its work being spread more? As you can see from the scenery around that we've been doing, we're basically working out of a garage here and producing equipment by hand out of the scrap yards. But that just shows that anyone can pretty much do this equipment if they have a basic engineering background and can put equipment together. But all in all, in summing up, we can say that there are very novel things that can be done by experimenting with Tesla's electricity. And this video shows that we pretty much discovered a lot of it as we went along. This wasn't prepared, we just sort of winged it and wanted to show a day in our lab with the experiments that have been going on. In the future, we will have much more coherent and practical demonstrations for people to carry on with. So I'd like to thank you all for watching, and we will be back from our top secret laboratory again sometime in the near future. Have a good day.